All right, so let's consider next the using that solar radiation for heating, and next week we'll consider it for making electricity out of it. So if of that incident radiation, falling on this guy and he's sitting here at latitude till all year long, receiving that radiation, the question now is how hot will the water get? How effective those solar heaters are in heating our water. And I remember when I was still a graduate student, my supervisor, he was working as a consultant for a rowing club, and they wanted to have solar heaters for in their rowing club, and they wanna like make him like supervise the project, and he straight ahead told them, don't buy solar collector, just buy electric heaters, and or natural gas, I forgot what is, but he said no, don't even consider solar collector. And the reason was people do the rowing thing before they go to work very early in the morning, and then they come and take the shower before the sun even come out. And so what is the point? The sun will never be there when you actually needed it. Okay. So having said that, there are examples where the sun will actually be there when you're actually needing it, right? So let's see how we can calculate how hot the water will get. So there are two kinds. There is kind which have pipe into it. So the water come and go into pipes back and forth under that black, under this glass covered with a black collector. So there's a black wall that the absorber basically, the sun come and get absorbed by that black coating, and we will go to extend to make that coating really absorbent. And we'll understand what does it mean in a minute. But the pipes are connected to this heater, this collector, and they get hot, and the water go back to the tank, and the cycle keep going until the water become really, really hot. The other design is that rather than having pipes that may get blocked, you actually send the water between two plates. Just two plates, right? Black plate and black plate on top of it. And this is called flooded design. So, so either flooded or tube. And it doesn't have to be water, by the way. People can use liquid with antifreeze so that they don't have to worry about it in the winter. All right. But also you can just use air, because that solar collector could be used to heat air that go into the building downstairs to heat the building. So rather than using electricity, you're just basically using the sun to heat the air for space heating. So you'll find chart that's in this chapter for water and for air solar collector, and the air one is just for pure heating. So again, we saw this graph before. This is the sun radiation outside, the extraterrestrial radiation, and then the small curve is the sun in our Earth's surface. Okay, and here I'm trying to say that, well, the sun, most of the radiation of the sun is in the is in the visible range, which is really amazing how the sun and our eye are actually sensitive in the same range. So it's either our eye was developed for the sun or the sun was created for our eye. Whatever the case, it's a perfect match. So our eye is really sensitive where the sun is. Okay, but when the things are not as hot, they would peak in the infrared range. Okay, so if I turn off the light in this room, I'm not going to see you, right? But if I put my infrared goggles, you will be glowing in infrared. Why? Because your temperature hopefully is like in the, in 89 range, something. So in the 89 range, your curve will be like this. You will be glowing in the infrared. Okay, so the same thing for our car chairs. Our car chairs, all the furniture inside our car, when they radiate back, so the sun hit them in this range, but then when they get hot, they radiate back like this. So now the glass that is the cover of our solar heater and the glass that's the cover of our windows in our car behave differently for the wavelengths that's coming through it. So when the sun sends its radiation, it goes through. It's very transparent. So that's called transmissivity. Huh? How much you get transmitted through the glass. But when it comes to the radiation that's coming at the infrared range, the longer wavelengths, the glass become basically kind of opaque. He will not let it go. And that's why the car become really, really hot in the summer. Okay? I'm originally from Egypt, and over there, if I forget and crank if my windows are closed in my car, and I try to go into my car in the summer, I can't. Like I cannot touch the driving wheel from how hot it is. You always have to open the window a little bit, because if you close the window, the car becomes so hot, like you can burn your hand touching the steering wheel. Of course, the problem, like when you open the window, is that you get covered by dust. So it's either the car will be dusty or the car will be hot. So I mean, you choose your poison, basically. But the point is, the glass is very effective in letting the sun go in and wouldn't let the radiation leaving the inside. Why? Because the inside is not as hot as the sun. Of course, if the car is burning inside and fire and stuff, yes, that radiation will go through. But until you hit that point, the glass will block it. And that's why those solar collector will have a glass cover on them. Not just one, some of them have two glass cover on them, one and the second. Why? Because they want to make sure that really that effect get doubled. Okay, so for any transparent surface you get, when the radiation fall, that eye normal that we just, or eye tilted on our plate that we hit our surface, when it goes through, not all of it will go through. Some will go reflected. That's the reflectivity alpha. And that reflectivity becomes more and more if the angle is, if the incident angle is not 0, but like really big, like 50 and 60 and 70, then all the radiation will bounce back. That's how optical fiber work, that the angle is so small that the light never leave. The light get delivered on one side and go to the other side on the other side of the ocean. Never leave the fiber because it's keep reflecting from the inside. So reflectivity take a punch, right? And then the rest, some will get absorbed alpha, and the other will get transmitted tau. Okay, so one will be equal to alpha plus rho plus tau, absorptivity plus reflectivity plus transmissivity. Of course, if the surface is opaque, there is no transmissivity. It's only alpha and rho. So the black sheet at the end, that's opaque. He will not have transmissivity for our wavelengths, right? He will just have reflectivity and alpha. So you want him to be very absorptive, but not reflective. So the black color shouldn't be shiny. It should be like a really dull black. It should be a black coating that is like so depressing, like he's not shining at all. He just like take the light and never let go, basically. Okay, so now the other thing that we need to know too is that the radiation of the sun is just like a black body radiation at 5,800 Kelvin, black body. So black body radiation is represented by the sigma T to power 4. So the radiation scale with T to power 4. Sigma is Stephen Boltzmann constant, 5.67, 10 to minus 8. It's very hard to forget this number, right? 5.67, 10 to minus 8. How easy it is to remember. Watt per meter square Kelvin to power 4. So sigma T4, that's how much, if you give me the temperature, I will tell you how much radiation, watt per meter square is coming out. So now this is for a black body. The rest of the bodies are not black body, they are gray body, which is black multiplied by epsilon. Epsilon is their emissivity. Okay, so we like our black coating or the collector to have very big alpha and very small epsilon. Alpha will determine how much of the radiation he will absorb. And epsilon, unfortunately, if epsilon is big, it will mean that he will radiate also like crazy. He will radiate with epsilon sigma to power T4. So he get a little bit hot to 100 degree C or something, and he will radiate epsilon sigma T to power 4. So you don't want epsilon to be high. Unfortunately, you can see that for a lot of material, the alpha and the epsilon are usually of the same order of magnitude. So you really want something that have big difference between alpha and epsilon. You want alpha to be really big and epsilon to be really small, right? And you still want alpha to be really big too. So you're not gonna do an aluminum film, for example, just because the ratio is 3. You want something like this. This is perfect. Black chrome, 95 alpha, 0.15 epsilon, with this ratio 6.47. That is the ultimate goal. So just regular black plate when alpha and epsilon are the same, that is not good, right? Yes, absorb, but he will radiate them back. What? I don't want that. All right. So with the right black coating and with the right glass cover on top, something that have small. So by the way, now new windows on car, they tell you it's selective, just like selective coating for the black plate. They tell you the glass is like special glass. How is it how it's special? He will radiate both way. Like you will let the sun come and you will also let the seat send the radiation back. So the car wouldn't get as hot in the summer. So now with the right collector paint and like the right glass cover on top, hopefully the radiation will come and we will use it. We'll use it all for heating the water, going in as cold water and leaving out as really hot water. So that ratio between Q useful, and it's in watt, multiplied by the incident radiation on the tilted plate, we call it IT here, or I beta, or whatever, the tilted radiation, the radiation falling on you as a collector, multiply by your area, because this is watt per meter square. We're gonna get this one on the table, multiply by cosine theta I, you know exactly how much is falling per meter square, multiplied by our meter square. That's how much watts are coming in our surface. Now, how much is gonna be absorbed? That's key useful. The ratio is the eta collector. So like normal efficiency is always output over input, okay? So now he will try to develop a model for this efficiency of the collector. And I'm gonna cheat and I'm gonna show you that equation up front because we don't have this much time before the break. And we will go through this equation one more time. So the equation will look like this. It has a bunch of constants. We'll explain what they are, but it's also function of the temperature that you would like to get minus the temperature of the air divided by the incident radiation. This equation for the collector efficiency is basically this straight line. So this equation basically say that if you want to get to very high temperature, T average minus T ambient, you want the water to become, 120 degree C. You wanna make tea out of it, not just swimming pool. The efficiency will be 0. And why? Because the collector will start losing heat. If he's really hot sitting in a very cold environment, either because he's really hot or you are putting this in North Pole. T ambient is really, really cold. So if this range is really big, the efficiency would be 0. And the efficiency would be maximum when you don't want that water to be that hot. Okay? Meaning that the water is going in the collector very quickly. Go in, take 1 degree up, get out. The efficiency will be 100% almost. Because the water doesn't have a chance to get hot the collector doesn't have chance to get really hot, to lose money. You know, as if you are really rich, you can start losing money by spending on like really trivial stuff. But if you are poor, the efficiency of keeping your money is 100% because you don't lose it. You know, like kind of. So do you see a graph here for the one cover selective? So that's a glass cover selective. One cover black if the coating of the collector is not selective material, just a black coating with epsilon equal alpha. Less worse, huh? So that's why the paint makes sense. You know, you spend money on the paint, the efficiency get higher because the collector take the heat and never leave it, never lose it. That's why you can go higher. And this one is zero cover. How is that possible? The collector is just a black surface where the pipe goes through and basically go back to the place where it's collected at, the tank, which is the swimming pool. So you could say, well, that is a horrible efficiency curve, right? Because it does not go that high. But what if you don't really want to go that high? Maybe you just want those people to feel a little bit warm. You don't want to boil them alive, right? You just want to get them a little bit warm. Then the difference efficiency would be like between 0.8 and say point, depending on how hot you want, 0.8 and 0.5. Okay, and also notice that the efficiency is telling us Q useful divided by the incident radiation, which is for free. So that efficiency is telling you are getting 50% of something free, or you are getting 80% of something free. At the end of the day, what does it really matter? It doesn't really matter when for the price of the cost or the price of the fuel. What matters is if you have really lower efficiency, you have to make really big collector. So when I go to low and I have two PV panel for my RV, and one of them is saying 30% efficiency and it's very expensive, and the other one is saying 15% efficiency and is way cheaper, which one I should buy? I should buy two of the 15%. Why? Because all it cost me is extra space on the roof of my RV. So if I just have extra space and I'm not running out of space, then I don't matter. It doesn't matter, right? So the efficiency is Q useful divided by incident radiation times the area. So if the area is there, you don't really worry about the incident radiation. And at the end of the day, most of those renewable sources, what really matter is not the efficiency. It is the levelized energy cost. How many dollar per kilowatt hour? How many dollar during the span of the project per 1 degree C heating in my pool? That's what really matters, not the efficiency. All right. So a solar panel that's 30% efficiency and it's like 10 times expensive than a solar panel that's 10% efficient doesn't make sense. All right? Because if the price is really big, then the price per kilowatt hour would become really expensive. Okay. Of course, it does help if the efficiency is higher, so things can become smaller and become cheaper. But what I'm saying is that the ultimate decision or the judgment is the cost per kilowatt hour. Not the initial cost, not the efficiency, not the mile per gallon. Okay, good. So let's take a 15 minutes break and we start the exam exactly at 9 o'clock. Okay.